Last time, I consider last time to be kind of the end of the real material for the semester, but I wanted to talk today about something kind of fun. I think it's fun. You'll see if you agree. Fun with series. I hope that we can get. I hope that I can get to the punchline by the end of class today. If not, we might hang a few minutes next time. But this is inspired by one of my favorite facts from real analysis that actually we never got to, because it has to do with series, which is a we could have spent many times talking about series, but I decided not to do other stuff. There's just not enough time. A lot of universities do 2 semesters worth of analysis, and then you can do lots more stuff. But anyway, I actually saw a math tweet a few days ago where somebody asked the internet, is real analysis just like some kind of exercise in formality where we just do all the same stuff from calculus again, but written with more epsilons or whatever, or do we actually learn anything new by doing real analysis, or is it just all the same old stuff but written in a different way? And one of my favorite facts about real analysis is something that I feel like is not really possible to discuss unless you know something about analysis. And so that's what I'm hoping to get to today. Anyway, a little fun with series. I know series is something that you all talked about in your calculus class, but I'm pretty sure that you did not discuss this fun fact that I want to get serious about here. So let me just refresh our memory about what a series is. A series is it's what you get when you add up all the terms of a sequence, an infinite summation. A series is a sum like this, sum of an, where an is a sequence. So a series is what you get when you add together infinitely many things. And you could say usually when you add together infinitely many things, the answer is infinity. The series doesn't always converge. It often diverges, but let me just say sometimes it converges. Sometimes it doesn't. Sometimes not. All right. But I think you talked about in your calculus class a few simple types of series. Probably one that you discussed is this, the sum of 1 over 2 to the n. There's a name for this one. This is called the geometric series. And just like usual in this class, when I write the sum, I'm gonna start at n equals 1 and go to infinity. That's always what we do, just because it's a sequence, right? You think of this as a sequence, and then I'm going to add together all the numbers in the sequence. So I'm never really going to write n equals 1 to infinity, but that's what I mean. Anybody remember this from your calculus class, perhaps? Anyone know what this adds up to? If I were to write out the terms here, starting n equals 1, this is a half plus a fourth plus an eighth. It's the sum 1 over the powers of 2, all of them. Yeah, this adds up to 1. Actually, this is not so hard to see if you just, I'll try and sort of draw a little picture here. This is the interval 0 to 1. And if I add these numbers up, 1/2 goes this far, right? That's what half. I'm going to imagine stacking little intervals of those widths next to each other. If I stack in a 1/4 to the right of that, it goes like this. Actually, because of how these numbers add up, this 1/4 kind of evenly cuts the difference at the end of that little interval, right? The next one I put in would be an 1/8, which again cuts this distance here evenly in half. So this is an 1/8. Then a 16th would again cut this in half, right? And I think it's not so hard to believe me if I told you can actually fit all of these, even though there's infinitely many of them, they all squeeze in right here. And in the limit, it actually does add up to 1. So this here equals 1, all right? this is called the geometric series. This specifically is the geometric series, which uses a 2 here. If you use a different number there, it also converges, and there's a formula for what it converges to based on what that number is, which we don't need to get into. But anyway, the geometric series is an example of a series which converges to a 1. Here's another example. Just 1 over n. This has a name also. This is called the harmonic series. So this would be 1 plus a half plus a third plus a fourth, etc. It turns out these guys, this series diverges. It does not converge. This actually kind of adds up to infinity. Even though the terms that you're adding in each time, they get smaller each time, they do not have a limit. This is still unbounded. This one actually diverges, I'm going to say, to infinity. What I mean by that is if you continually add those numbers up, the sums that you get every time, if you take only some of them, those things are unbounded. And just to prove it to you, well, I'm going to prove it to you in 2 ways. The first way is not a real proof, but I did a little Excel today. Can you believe it? This is a plot of adding together the first n fractions. What? So you can see here, it starts with 1. That's just 1, and then the next point here is 1 and a half. That's 1 plus a half. The next point is 1 plus a half plus a third, which apparently is right there. And as you go on, each time you add in the extra one little bitty bit. This it's hard to tell on the picture. It looks like maybe this has a horizontal asymptote, but it doesn't actually. This will continue to go up forever. So these little numbers, as you add them together, it diverges. All right. This is the harmonic series, and it diverges. That means when you add these numbers up, actually it sort of equals infinity. You get it is unbounded. All right. That's not really a proof. I wanted to show you how you could actually justify that really is unbounded. So technically speaking, the way that this is defined, and I think you probably talked about this in your calculus class too, this sum 1 over n is defined as, here's how we define it. You let's say Sn be 1 plus a half plus blah, 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 plus 1 over n. So this Sn is when you add them up only to a certain point and then you stop. All right? That is called the nth partial sum. I'm not taking all of them. I'm only going up to a certain point and then stopping. That's called the partial sum. And then 1 over n is defined to be, this is the definition, it is the limit of the Sn. So you consider just adding up some of them. You can add up to the 100th one or to the 1,000th one or to the 1,000,000th one. You take the limit as n goes to infinity of that. And that's what the definition of the series is. And anyway, in this case, this equals infinity in this particular example. But I want to try to explain why Sn in this case is unbounded. It's not so hard to see, although you have to do a weird trick, and that's that may be one theme for the day. Is I'm going to show some very weird tricks that you can do with series. But so anyway, Sn is, I'll just write what I wrote before: 1 plus a half plus a third, etc., up to 1 over n, right? The weird trick involves imagining that n was a power of 2. So if n is a power of 2. Let's say if n is like 2 to the power k, then you can actually do some weird tricks with this. So I'm going to write this again, 1 plus a half plus a third. Actually, I'm going to write a few more than that just to facilitate the weird trick. A fifth, eventually get up to an eighth, and so on. Plus, the last one will be 1 over 2 to the k, right? Because I am thinking of the partial sum when I'm going down to a power of 2. All right. And here is a weird trick, which no ordinary person would think of doing this, but you certainly, once you see it done, it's not so bad. You can group those terms also kind of according to powers of 2. So I'm grouping them together like in blocks, where each block goes up to the next power of 2. And so the last block actually goes, somewhere like that. All right? And then I'm going to do an inequality here. I'm going to say this is greater or equal to, I'm going to replace everything in each block with just the last number in the block. So that 1/3 I change to a 1/4, which makes it smaller. The next block, I'm going to make them all 8ths. And then the final block, I'm going to make them all 1/2 to the k's. All right. That's the weird trick. And can we simplify this at all? Actually, each of those blocks, you can add them up. That's a 1, that's a half. Can anyone say what is the sum in this block? We've got to add the fractions. 1/2, yeah, 1/4 plus 1/4 is 1/2. What about the next one? This is a bunch of 8ths, and in fact, if you think about where they came from, there are actually 4 of them, right? So there are 4 8ths here, so that's also 1/2. And if you think this through, you will realize all of these blocks add up to a half. Even the last one adds up to a half also. Here the denominators are 2 to the k, but how many terms are inside this block? It's a lot of terms. It's all the ones from 2 to the k minus 1 up to 2 to the k. That's 2 to the k minus 1 of them. Anyway, they all add up to a half. And so what do we get overall? This is 1 plus a bunch of halves. How many halves are there? It's the number of these blocks. And these blocks went up to 2 to the k. Again, if you think this through, I don't want to belabor the details. There's k different blocks there because we arranged the blocks according to the powers of 2, and we ended up with k different powers of 2 there. So there are k different blocks there. Anyway, so this is the end of this weird trick. So in conclusion, s sub 2 to the k is greater or equal to 1 plus k over 2. And that, my friends, is unbounded, right? This right here, as k grows, this goes to infinity. And that means that these sums are unbounded. So as you keep on adding stuff, more and more stuff to it, these sums are unbounded, which means that's why it goes to infinity, all right? Because as you continually add stuff to it, these sums are always bigger than this number, and this number is unbounded when the k increases. So this is like that, so the s, at least the powers of 2 are unbounded. That means automatically the entire sequence of sums, Sn, is unbounded because at least some of those are powers of 2, and those ones are unbounded, so the whole sequence is unbounded. All right, and that's why this sum 1 over n, the harmonic series, diverges. You could say it sort of equals infinity. When you add all those fractions up, doesn't converge to any particular number. You just get infinitely many things. It's unbounded. All right. That's the harmonic series, 1 over n's. What gets interesting and what I want to talk about today, I think I'm definitely going to have enough time. I'm trying to rush through the beginnings. I hope I'm not rushing it too fast. All of this stuff you probably talked about in your calculus class, although I don't know if you did that weird little trick. I would like to talk about the alternating harmonic series. And I have several more Excel charts to look at in relation to the alternating harmonic series. What that is, it's the same thing, but when you're adding those fractions, 1 over n, you alternate the signs every time. So it's going to be -1 plus a half, minus a third, plus a fourth, minus a fifth, plus a sixth, etc. So this series is the sum -1 to the n over n. This is called the alternating harmonic series. Alternating because the signs they alternate back and forth. All right. And I want to talk for our remaining time together about this series and whether it converges or not. Actually, sorry, I meant to say something before this. It's all right, we can do this slightly out of order. Remember, the sum 1 over n diverges. That would be if they were all positive, right? If they were all positive, that just kind of equals infinity, all right? What if, something I meant to talk about before alternating the signs, what if we took only the even ones? Would that still go to infinity? Or would only the even ones somehow, like I want to think about what exactly about this makes it go to infinity? Is it the even ones or is it the odd ones? The answer is kind of like, well, it's not either of those, it's just the whole thing goes to infinity. But if we thought just about the evens, just the evens, this would be, 1/2 plus 1/4 plus 1/6. That's smaller, right? This sum is less than that. I mean, it has less stuff in it. I just omitted half of the stuff. Maybe I get half of infinity this way. You should not feel comfortable about people saying half of infinity. But this, if I were to write it as a series, it would be like this, right? 1 over 2n. What do you think? If I already know this thing diverges, any ideas about that? I think, anybody feel like you can actually do some simplifying things with series? You've probably seen this before. Can you? Yeah, you should be able to pull the 1/2 out, right? If there's any justice in this world. This should be true. And actually, it is true for series which converge. You can factor out a constant, all right? What that means is that if this one is infinite, then this one is also going to be infinite, right? Just factoring out a 1/2, you're still going to get something infinite over here, all right? So this, the sum 1 over 2n, also diverges. All right. Another way of saying that is if this converged, then you would be able to factor out the 1/2, which would automatically mean that this also converges, but it doesn't converge. So that means that they both have to diverge. All right. So if I take only the evens, it diverges. What if I take only the odds? That also diverges. I mean, the trick of factoring out doesn't work as cleanly, but would you believe me if I said also just the odds also diverges? This is going to be important to what we say in the future, all right? But if I take only the evens, that is infinite. If I took only the odds, that also is infinite. And of course, when you take them all together, the whole thing is infinite also, all right? Okay, anyway, let's go back to this alternating harmonic series. So in the alternating one, I have -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5 plus etc. All right. You could think of this as like a battle between the odds and the evens. I have made all the odds negative, but kept the evens as positive. And since the evens diverge, the evens just taken together go to infinity. But the odds also go to infinity, and since I'm subtracting them, it's kind of like, I would say, just the evens make it go to infinity, but just the odds, since they're all being subtracted, would make it go to minus infinity. There's sort of like a kind of a tug of war sort of situation here, right? The even parts are making it want to become positive infinite. The odd parts are making it become negative infinite. So maybe this one actually cancels out and gives you 0. It doesn't actually give you 0. Like you can tell, these numbers do not actually add up to 0. But there is actually kind of a give and take, which makes it so that this converges. And it's not so hard to see, even if you're just trying to do this by hand. I'm going to try to draw a little bit of a plot of these points. -1 is the first one, which would be down here, right? minus 1. But then the next one would be minus 1 plus a half. I'm just going to try to draw what happens if you just try to add up some of them. Minus 1 plus a half, that goes up to there, right? Went up by a half. And then the next step goes down by a third. That goes down, but only sort of a little bit, I guess, to there, right? It doesn't dump down below here because it had gone up by a half. It goes down by a third. And then it goes up by a fourth, so that's sort of up a smaller little bit, right? Each time I'm going the other direction, but it's an increasingly small number. So actually it seems like this really will kind of do something like this, and it seems like that's going to converge, right? Although it's not going to be to 0. I mean, you can tell even on my picture, it's definitely not going to converge to 0. It converges to some number that's between -1 and 0, but not 0 itself, all right? I did this on my Excel. This is what Excel is good for. I use Excel for my grades and also silly pictures like this. Yes, this is the one. I have several in there. This is the real graph of what I was just trying to draw by hand. It starts at -1 and then just kind of does this jiggity jaggedy thing. But anyway, it seems that this is converging. Actually, it turns out, and this is kind of difficult to prove, and I don't want to get into the details of this, but it turns out the sum -1 to the n over n, it actually converges to a number -0.69 something something. This, it turns out, is actually equal to negative the natural log of 2, which I think is a very strange and interesting fact, that you add together a bunch of fractions and they add up to this weirdly specific irrational number, -0.69, etc. It is the negative the natural log of 2. Strange but true fact. I said that today we would talk about something that you can impress your friends with your new knowledge. This is not really there yet, but this is the beginnings of your new knowledge that will impress your friends. When you add up this series, you get this weird number. All right. This is not all that shocking. I mean, it's weird, but it's because this series involves kind of a positive infinite part and also a negative infinite part, and they sort of balance each other out, although not to 0. They balance each other out to this weird number. All right. I want to play a little more fun, weird tricks with this. So they balance out. This is what I'm trying to say. But I'm going to say it's a little delicate, the balancing. For example, what if we add them up? What if we add 2 odds at a time? What I mean by that is -1 minus a third, and then plus a half, and then minus a fifth, minus a seventh, and then plus a fourth. I'm still adding the same fractions together, but I take I'm taking the negatives 2 at a time, and then 1 positive, and then 2 negatives, and then 1 positive, and so on. So next will be minus a ninth, minus an 11th, plus a 6th, etc. All right, the same values, but I have rearranged them in a weird way. What are your thoughts? Anybody has thoughts about this? What if I were to try and draw a similar chart as before for this one? You know, this chart right here, right? This was perfectly alternating them. A positive, then a negative, then a positive, then a negative. Actually, the first one was a negative. What about this way? Any thoughts about that? Am I going to get the same chart? I mean, it's not exactly the same because, for instance, the first number will be -1. That is the same, but the next number will be negative a third. What do you think?
Well, I was going to say it seems like it's instead going down, so they'll converge to a different lower number.
Yeah, it seems like this thing, if anything, it's going to be down here, further down. at least towards the beginning, because towards the beginning here, there's like more in the first, say, 5 terms, there's more negative stuff than there used to be in the first version that we did this, right? Because I'm taking 2 negatives for every positive. This, she says, should be further down. Can I just say each partial sum, you know, like the Sn, that is, if you only add up, say, the first 5 terms or the first 10 terms, it's going to be lesser this time because the beginning will be stacked with more odds, which are negative, than there used to be. So each partial sum here will be less than before, right? And what that means is that what it converges to will be less than before. In fact, I drew this on the Excel, all right? So I took the same numbers, but in this order, taking 2 odds and then an even, all right? And this is my picture. I decided to put them together. So the red one is the same one from before, but the green one is this new one where I'm taking two odds for every even. It's further down, all right? And it's not, these are not going to converge to the same thing, all right? The moral of the story is, and this is what you can tell your friends, in an infinite sum, I don't know if your friends like infinite sums. This may be a turn off immediately for them, in which case just keep it to yourself. But I've learned this the hard way in my life. In an infinite sum, rearranging the terms, that is, adding the same stuff but just in a different order, can change the value. This is very interesting to me. And I remember this kind of blew my mind as a young lad when I learned this. In an infinite sum, rearranging the terms can change the value. This goes against the traditional sort of commutative property of addition, where if you change the order of a sum, it doesn't matter. This is true for finitely many things. I mean, usually we just use that for 2 things. You can interchange the order. That's the commutative property of addition. But it is not so for infinite series and what they converge to. Yeah.
Isn't that because this is partially subtraction too?
Because there are some subtractions. Yeah, actually, if it is a fact, if all the terms were positive to begin with, then rearranging it will not change the value. Although it's hard to say what. Maybe you're thinking of because there is no commutative property for subtraction. Is that what you're thinking?
Yeah.
Like that's definitely there's no commutative property for subtraction. Like 1 minus 7 is not the same as 7 minus 1, right? But when I say I'm rearranging the terms, I'm not talking about that. I would think of this as 1 plus a negative 7, and then this really is the same as a negative 7 plus a 1. Like when I'm writing these numbers in a different order, but I'm still bringing the signs with the proper signs with them. It's not like I'm changing a negative into a positive by rearranging the order. They still have the appropriate signs are next to them. Yeah. Anyway, this is the big punchline. Rearranging the terms can change the value. And right here, in fact, when you add in this specific way 2 negatives for every positive, anybody want to guess what this converges to? There really, if you're even still paying attention to this point, really there is no way of predicting what this. I mean, if this one converges to negative natural log of 2, in my opinion, I have no prayer of guessing what this one converges to. The answer is negative infinity. Actually, this one diverges. It goes down forever. So not only rearranging the terms can change the value, it can change it from being finite to infinite. All right. So this one here, this green one here, when I go 2 odds for every even, actually will diverge to minus infinity. Would anyone like to suggest? Is there a way, do you think, you could make it diverge to positive infinity by rearranging? Yeah. Yeah, if you took 2 of the evens and then Yeah, 2 positives for every negative, or 2 evens for every odd. That one would actually diverge to positive infinity by rearranging the order in that way. It would go, it would start off in the same place, but then go up forever, right? Very strange. Yeah.
Is this like kind of because, how like the real numbers and natural numbers are both infinite, but there's like real numbers, there's still more. It's like there's 2 types of infinity. Is there more, in a way, of the positives than the negatives, so it goes to infinity?
I don't. So this has nothing to do with countable versus uncountable. Although I would say one way to explain this is when you look at the series as a whole, it is all the same numbers. All I did was rearrange the order. But if you only consider, say, the front part of it, actually any finite chunk of them, when I do it this way, has twice as many negatives as positives, which is not true of the original way around this way. If I only take the first bunch, it has an equal number of negatives and positives. But when you rearrange it to this way, you're sort of front loading all the negatives, which makes it it becomes super negative before the positives are ever able to catch up. And then you can, the same way, you could front load the positives and make it go to positive infinity. Did you have another question?
I was just gonna say, like, this is just like hypothetical, but do you know what happens if you're like negative, positive, positive? Would that also be something different, or?
I think that would probably give you this again.
Okay.
Yes. So if you, in order to actually get a different answer, you have to move things by a lot. Like, for example, what she just suggested is if we just do 2 negatives and then 2 positives and then 2 negatives, that's the same as if I were to just swap individually like this, right? That would not change the sum. If I only consider, say, the first 100 things, it's still the same answer as it was before. The reason it's really different here is because when you add up the first bunch of them, it's really going to be quite different because I have more negatives than positives. Yeah. I have just a couple more things to say about this. I have plenty of time. So, the moral of the story, I wrote it down already. In an infinite sum, rearranging the terms can change the value. The value we've seen so far, it could be negative natural log of 2, or it could be negative infinity or positive infinity. Could we make it add up to some other, make it converge to some other specific value? Actually, you can. I will show you on the Excel. How about this one here? This is, again, those same terms written in a weird order. What I did here was I started with a -1, and then I added a bunch of positives. I added, I guess, 1, 2, 3, 4 positives until it went up to here, and then I added 1 more negative, and then 4 positives and 1 more negative. Although it's not always 4 positives, like right here, you can see I only added 3 positives. I don't know if you can see the little dots, but it's not always the same. But my strategy in adding these together was I took positives until it goes above 0, and then I add 1 negative, and then I add positive, positive, positive until it goes above 0, and then 1 negative, and then positives until it goes above 0 and 1 negative. The effect is this strategy, what is that going to converge to? It's going to converge to 0, because I am specifically taking these numbers so that they just barely make it above 0, and then I dump it below 0, and then build it up again so that it's just barely above 0 and then goes below 0. You might wonder, how are we sure that it's always possible to get back up to 0? Maybe we dump it too far and we can just never make it back to 0, but actually you always can, because the positives by themselves go to infinity. That means we have sort of an infinite well of positives to draw from, which can make it go back up to any value. So this ordering, this one converges to 0, right? You can choose the ordering in such a way that you get it to converge to 0. Or here's another example. Here. This one I used a lot more dots. This one I made it converge to 1 by the same strategy. You add a whole lot of positives until it goes above 1, and then you add a single negative, and then you add a whole bunch of positives, get back to 1, add another negative, and so on. This one converges to 1, right? The fact is, you can, however, whatever number you want, you can make it converge by rearranging the terms in some weird ordering. All right, you could make it converge to pi if you wanted to, by doing this same trick. You keep on adding positives until it goes above pi, and then you add a negative, and then you keep on adding positives to make it go above pi. So here's this. I will just leave you with this big theorem about the alternating harmonic series, and it's not just this example. There are many examples, and there are lots of more serious theorems about this. But anyway, for any c, a real number, or c equals infinity, or c equals minus infinity, there is some rearrangement of the series which converges to C. All right. For any number that you like, you can rearrange the terms so that it makes that number. You could make it add up to 1,000,000 exactly if you wanted to by a rearrangement of the series. All right. Actually, this is true. It's not just this alternating harmonic series. That's the simplest example of a series like this, but this is true for any series where the sum of absolute value an diverges, but the sum of just an converges. This is the general theorem about this kind of a series. If you have a series where the series itself converges, but if you were to make all the terms positive, it diverges, that is true of this series. This series by itself converges to negative natural log of 2, but if you make everything positive, then it goes to infinity. Any such series also has this property. Those series, you can get any answer you like by rearranging the terms. And that's it. She just left. She's going to come back. We'll all be done. That's all I wanted to say. This is an interesting fact in my opinion. I hope it's interesting to you too.